Okay, thank you for introduction. And, I'm very happy to have a talk here today. So my talk consists of following 4 topics, but before that, I would like to briefly introduce what is space weather and ask you a question. So what is space weather? So Marx already mentioned about that. So according to Wikipedia, space weather is a branch of space physics and aeronomy or heliophysics concerned with the time-varying condition within the solar system, including the solar wind, emphasizing the space and surrounding the Earth. So basically, there is no wind, no shower in space, but the solar wind and the X-ray shower exist. So that's why we call space weather. And these cause many problems, such as radio wave disturbance, electric grid disruption, and also today's topic, astronaut safety. So the question is, does the radiation dose of Mark Watney in the movie The Martian exceed the JAXA carrier dose limit? It's a 0.8 sievert for 40 years old male astronauts. Actually, how many people watched this movie? Please. Oh, a lot. Thank you. So, as you know, he departed from the Earth and spent 124 days in spacecraft in deep space and arrived at Mars and had an accident and need to stay in Mars for 563 days. And he was rescued from the Mars and spent 124 days and returned to the Earth. So how do you think? If you think his dose is over 0.5 sievert, 0.8 sievert, please raise your hand. If you think no, the answer is no. But it's very close to. So, according to the recent observations and simulation, the dose inside a deep space mission is about 1.84 millisievert per day, and dose on the Mars is 0.6 millisievert per day. So in total, 790.4 millisievert. Of course, this is imaginary missions, and the dose really depends on the solar activity. So. But we can say that the precise estimation of radiation dose is very important for deep space mission. Okay, so now I'd like to move to the main topics, and first I would like to introduce the radiation environment in space. So here, Mark also shows a similar movie, much more clearer. But I like to use this picture, and the radiation environment in space is consists of mixture of particles from solar and galactic origins. And for example, at the interplanetary space, photons, including X-ray, UV, visible light, and solar wind, it's a plasma of protons and electrons continuously emitted from the sun. And in the magnetosphere, trapped electron up to a few MeV and a trapped proton up to a few hundred MeV exist. And in addition, galactic cosmic radiation, so-called GCR, up to extremely high energy, up to 10 to the 20 electron volt, continuously come to the heliosphere. And in addition, sometimes cause coronal mass ejections and emit solar energetic particles, so-called SEP, up to a few GeV. And here is a typical energy range of each cosmic radiation. So this is particle energy and fluence, flux, and flux of solar wind protons, auroral electrons, trapped proton at the outer zone, and also solar storm protons. These particles have very high flux, but the energy is too low to penetrate the spacecraft shielding. So basically, they cannot contribute to those. And only trapped protons, solar flare protons, SEP, and galactic cosmic radiation can penetrate the shielding and contribute to the dose. So this slide shows a typical cosmic radiation dose calculated by the Fitts code at the solar quiet period. That means no SEP contribution included. And as you see, the cosmic ray dose becomes the largest at the lunar surface because no physical and magnetic shielding there. And dominant contributors are different for each environment. For example, at the sea level of Earth, muon has a dominant contribution. At the flight altitude and Martian surface, neutrons has a dominant contribution. Inside ISS, proton has a dominant contribution because trapped proton exists there. And at the lunar surface, heavy ions has a dominant contribution. So there is no simple way to protect the cosmic ray exposure effectively for every environment. That's radiological protection for astronauts more difficult. So this slide shows a temporal variation of each cosmic radiation. So GCR and trapped proton always exist, but SEP temporarily only when a large solar flare occurs. So temporal variation of GCR and trapped proton is gradual by 11-year period due to the solar activity cycle. On the other hand, temporal variation of SEP is impulsive, only a few days, due to the coronal mass ejection. So dose rate of GCR and trapped protons are always low and rather predictable, but a SEP dose rate is occasionally very high and unpredictable. So that's why the progress in space laser research for SEP dose estimation is desirable for ensuring the radiation safety of astronauts as well as air crews. So there are two major space weather topics on this issue. One is the detection of and alert to solar particle event, and the other is the estimation of the worst case scenario. And I would like to talk about the detection and alert first. So for detecting SEP, there are two methods, and one is by satellite observation. This graph shows proton and X-ray flux measured by GOES satellite on the geostationary orbit during the solar flare event occurred in September 2017. In general, the solar flare class is indexed by the X-ray flux, like B class, C class, M class, X class. And in these weeks, many X class and M class flare occurs. It's quite rare, but only the last one associated with the large solar proton event. So that means proton and X-ray flux are not well correlated with each other. So, and SEP dose cannot be estimated from the solar flare class. So this makes the prediction of SEP dose more difficult. Instead, occurrence of solar flare itself is rather feasible based on the recent AI technology. On the other hand, the accuracy in measuring high energy SEP above 100 MeV is not so good. So we need to use another device to detect such high energy SEP. It's a Neutron Monitor. So Neutron Monitor checks the variation of cosmic ray flux above a few hundred MeV that can generate neutrons penetrating to the ground level. And here is a map of the Neutron Monitor, and real-time data is available from Neutron Monitor database. And this graph shows the count rates of all stations in Finland during the week I showed before. And as you may remember, there are many solar flares occurred in this week, but count rates even decrease in the middle of this week, so-called forward decrease. This is because the strong magnetic field of solar wind emitted by the solar flare prevents Earth from the GCR exposure. And the count rates increase only when very high energy sets are incident to the Earth. Here, we call ground level enhancement, GLE, for this. And it can be used as an alert to the SEP exposure. So there are several systems for use for alert system for aircrew exposure, such as NIRAS developed by NASA, and Abydos developed by ESA, and Wasabi is developed by Japanese Institute. And the NIRAS and Abydos use the GAUSS data as the input data and extrapolate the data to the ground direction using the magnetospheric and atmospheric SEP transport simulation using the vertical cutoff rigidity and HD Tran or Furuka code. On the other hand, Wasabis use both GAUSS and Neutron Monitor data, so it's interpolate between the ground level and the geostationary data using the magnetospheric and atmospheric SEP transport simulation by Chiganenko 89 model and our developing Monte Carlo code fits. So actually, Wasabi is very recently open to the public, just a few weeks ago. So if you're interested in this system, please check the website. Then you can easily find Googling the Wasabis in your browser, I think. Here is an example of the Wasabi's calculation. So set dose rate at 12 kilometers during the peak of GLE 69, the largest event occurred in 21st century. And the color assigned to each D index, for example, red area is dose rate above 80 microsievert per hour. So it means severe conditions. And the calculated SEP dose information is provided to ICAO, the International Civil Aviation Organization, in real time, and used as a mandatory information to operate their center. For aircrew dosimetry, it's rather feasible to do some countermeasure against SEP exposure, for example, reducing the altitude or maybe even cancel the flight. But for astronauts' case, it's very difficult to do that. So estimation of worst scenario is very important. So for that purpose, there are several software, and the widely used one is Altaris, developed by NASA, and Spenvis, developed by ESA. And they contain the SEP fluence for historically large GLE, evaluated by several authors, and they can consider the influence of the magnetosphere and spacecraft shielding effect. So they are currently used in space mission design in many countries. Here is an examples of the SEP fluence provided by Altaris. And the hardness of the spectrum depends on GLE very much. Some GLE is quite hard, some GLE is not so hard. And GLE occurred in February 1956 and October 98 are the hardest event and frequently used as the worst scenario. But those spectrums are evaluated by rather old models. So recently, they are re-evaluated by Tilka et al. Using the function of double power law in rigidity, so-called band functions. So here is the re-evaluated data. So spectrum of February 1956 is not as hard as it was expected, but still the hardest one after the modern solar observation was started. And in addition, recently the probabilistic models to predict the integral SEP fluence during a certain space mission, considering the confidence level, solar activity, and mission duration. So this graph shows the mission integrated SEP fluence at 95% confidence level, predicted by various models for 2 years, for 2 years and 7 years missions. And these models enables more sophisticated mission design rather than simply estimating the worst case scenario. So here comes the question again. The models for estimating the worst-case scenario and the probability of integral self-fluence, as I showed before, were developed based on the modern solar observation after 1940s. So, is the worst-case scenario estimate from this model really the worst scenario that the sun can cause? So, answer is, of course not. So, the sun has a history of 4.6 billion years. So, 100 years is nearly nothing for sun's history. So, the next question is how to estimate the past solar activity. In the current technology, past solar activity can be deduced from the cosmogenic nuclide yield from the tree rings and ice core. And recently, my friend Miyake-san discovered a sharp peak of carbon-14 yield in the tree rings in AD 774-5 and 993-4 due to extremely large solar particle events. So here, the spike here. So it's in general, cosmogenic nuclides are created by galactic cosmic ray, but extremely large solar particle event occurs, so it also creates cosmogenic nuclides, so and increase level of yield for a short distance. So, how large the astronauts dose when such extremely severe event occurs? So, another recent observation of cosmogenic nuclide yield suggested that the self-fluence for AD 774-5 event was estimated to be approximately 119 to 141 times higher than the GLE 69, the hardest one occurred in the 21st century. And based on our Wasabi's simulation, if a male astronaut had stayed in an ISS-type spacecraft in deep space during GLE 69, his red bone marrow dose and dose equivalent would have been 5 milligray and 8 millisievert. So, if you simply multiply these two values, you can say that the astronaut's dose may exceed the threshold value for some tissue reactions, 0.5 gray, and their carrier limit, so 0.6 to 1.2 sievert, depending on age. So, this is the last slide before conclusion. So, even using the cosmogenic nuclide yield, you can trace back the solar activity only a few thousand years. So, another friend, Shibata sensei, hit on a really smart idea that the solar observation for like 100,000 years is equivalent to 100,000 solar type star observation for 1 year. And actually he did, and he analyzed the observation data from Kepler mission for 83,000 stars for 120 days, and found that the solar type stars can also cause extremely large flare, so-called super flare, which was believed to be impossible because hot Jupiter is a very big planet, very close to the stellar, is required to disturb the stellar magnetic field so much. So I don't think that we don't have to care about the super flare occurrence for like a realistic radiological protection, but as progress in space weather and astrophysics, we may need to consider the radiological protection against such super flare in future. In that case, not only for astronauts, but also the public on ground. Okay, let me summarize. So, 3 types of cosmic radiation, GCR, trapped proton, and solar energy particle, must be considered in the radiological protection of astronauts. And recent progress in space weather research has enabled a more sophisticated space mission design, considering the confidence level of self-exposure. And astronauts' dose may exceed the threshold value for tissue reactions and their carrier limits if once in a millennium class event occurs during deep space mission. So strategy of radiological protection against such very low probability but very high risk event must be discussed in future. That's all, and thank you very much for attention.
Thank you very much for a fascinating presentation on why weather in space is important and all the complexities therein. There are a couple of questions, you can see them as well as I can, from the floor. I'm sorry, from the app. But while I'm asking one, if people want to move to the microphone, please go ahead. There's one question about the ground-based neutron monitoring and whether or not there's any mountaintop monitoring to get a little closer to or further from sea level.
Okay, that's a very good question. And there are two factors to influence the magnitude of ground level impacts. So one is altitude, and the other is like a magnetic field. So polar region has weaker magnetic field, so basically better to observe. So the best place to detect the GLE is the South Pole, because it's a high altitude and also no magnetic field. So, and actually there is a Neutron Monitor in that South Pole. And other monitor, of course, Antarctic, and also it's a high mountain like Jungfrau also has one Neutron Monitor. So actually there is both high altitude and high latitude area.
Great, thank you. There's one other one that just came in about asking what's used to shield astronauts from space weather.
Excellent.
How do you protect astronauts from space weather?
That's, I cannot answer because I'm not belong to a space agency, so maybe Mark knows better than me.
No problem. A good question for the panel, perhaps, later today. Are there any questions from the floor? If not, then thank you very much.
Thank you.